I'm Rodrigo Martín Hernández. I'm PhD student at the Attostructura project, and I'm supervised by Carlos and Luis Plaza. I'm going to present my work about the generation of almost Fourier-limited attosecond pulses by the use of high harmonic generation process assisted by strong and ultrafast magnetic fields. So I would like to start with a brief introduction about high harmonic generation, which has been already introduced by Alba and Javier. And this is a highly nonlinear process which results from the interaction of intense laser beams with fast targets or solid targets and results in the emission of harmonics of the incident field up to the extreme ultraviolet or even soft X-rays. For example, it has been already demonstrated experimentally of the generation of harmonics up to the kiloelectron volt level using mid-infrared laser beams. To fully understand this process, we have to rely on quantum mechanics. However, as it was already mentioned, we can get a basic idea using the well-known three-step model. In this model, first we have the ionization of the atomic potential. Then this free electron will be accelerated by the electric field, and finally this free electron will collide with the parent ion. There will be a recombination and the emission of the harmonics. High harmonic generation has become one of the most popular sources for attosecond pulses, and although this popularity comes from its extremely coherence both spatial and temporal. There are other technologies for attosecond pulse generation, like free electron lasers. However, high harmonic generation still holds the record for the shortest pulse up to date, with a duration of 43 attoseconds. However, there is a fundamental limitation to achieve shorter pulses, and it comes from the intrinsic chirp of this process, or what we call the atto-chirp problem. For example, for this extremely broad spectrum, the Fourier-limited pulses that we could expect will have a duration of 2.5 attoseconds. However, due to the atto-chirp, it was demonstrated theoretically that actually the pulses that were generated had a duration of 1.2 femtoseconds. This means that due to the atto-chirp, the actual pulses were 3 orders of magnitude longer. To overcome this limitation, we propose the use of strong magnetic fields, isolated strong magnetic fields, to avoid this atto-chirp problem. As was already mentioned, the generation of isolated magnetic fields has been, there has been some proposals. And for example, from our approach, the generation of this in this kind of a scheme using the azimutally polarized beam interacting with the metallic antennas to achieve this isolated magnetic beam, as Luis Sanchez has shown before. So here we present a schematic overview of the system that we are going to study. First, we have the incident or the driving electric field that will interact with the gas target. And also we are going to assume that we have an external, isolated, strong, and fast oscillating magnetic field that will assist this process. It's important to note that this driving field will also have a magnetic field related. However, it will be orders of magnitude weaker compared to this external magnetic field. So we can neglect this, the contribution from this magnetic field. Here we present the Hamiltonian for this system. In the red box, we have the contributions from the electric field and the atomic potential, like in the standard scheme. And in the blue box, we have the contribution from this external magnetic field. As we can see, there will this external magnetic field will generate a kind of transverse harmonic oscillator that will oscillate on time. We have developed a 3D code to solve the time-dependent Schrödinger equation for the hydrogen atom. Well, here we present the actual high-order harmonic spectrum for the hydrogen atom with in the standard scheme without the magnetic field. Here, the intensity of the electric field is in the barrier suppression limit and is oscillating at 800 nanometers. We see that the cutoff frequency is around the 27th harmonic order of 40 electron volts. Now, if we have a magnetic field also oscillating at 800 nanometer and with an amplitude of 28 kilotesla, which is quite a high amplitude, we are able to modify the high harmonic generation spectrum in two ways. First, by increasing the yield and the generation of this second plateau. To understand why we have this kind of modifications, first we have started by diagonalizing this time-independent Hamiltonian. Here we present the energy levels that results from this diagonalization, and we can divide these energy levels in two groups. The first group, which are the bounded states or states with negative energy, that are almost unmodified by the effect of the magnetic field. The second group is these states with positive energy that without magnetic field, we should expect a continuous distribution of states like in a free electron gas. However, when we have this parabolic potential that comes from the magnetic field, we see that there is a restructuration of the states in the continuum. We see that the energy states are gathered around the energy levels of this parabolic potential. Here we have computed the distribution of the number of states, and this distribution is quite similar to the density of states of a quantum wire. So we can say that somehow with this magnetic field, we are creating a quantum wire in the continuum for the ionized electron. And this magnetic field will induce a restructuration of the energy levels for the continuum. Also, we have computed the transverse dynamics of the wave packet when it's under the action of this magnetic field. And what we see is that once the wave packet is ionized, then we have some spread of the wave function. However, there is a partial confinement, and we'll have this kind of focusing dynamics or revival dynamics. We can understand the yield increase that we saw before if one of these revivals occurs at the recollision time. Also, we have computed the time evolution of the population for the different states of this transverse harmonic oscillator. And we can see that once the electron is ionized, we have some manipulation of the population of the lower states. And this population will transfer to higher states in the transverse harmonic oscillator. As a result, these higher states of the transverse harmonic oscillator can also contribute to the harmonic emission, and we can understand the generation of this second plateau that we saw before. Now the question is, can we induce higher transitions in this kind of transverse harmonic oscillator in such a way that they can contribute to the harmonic emission? So here we propose the use of circularly polarized drivers along the external magnetic field to achieve this population transfer to the higher states of the transverse harmonic oscillator. Again, we start here with the spectrum for the hydrogen atom in the standard scheme with a linearly polarized driver and no magnetic field. And now the spectrum that we get when we have this with this novel scheme of circularly polarized driver and the external magnetic field. In this case, we have the same amplitude, 28 kilotesla, but now we have a wavelength of 1.6 micrometers. And this value for the wavelength is an important factor that we'll see later why. We see that in the case of this novel scheme, we have a much wider spectrum extending over hundreds of harmonic orders, even reaching the water window. Now we can filter out the emission below 100 electron volts to see how are the pulses that can be generated. So by filtering this emission, we see that the pulses that we can generate have a duration of 27 attoseconds. But the most interesting thing here is not only the duration, but also that they are very close to the Fourier limit of this spectrum. As we can see, the Fourier limit for the spectrum that we saw in the previous slide is 23 attoseconds. To get a better insight about how is this emission, we have also computed the time frequency analysis. Here we present the time frequency analysis for the standard scheme of the linearly polarized driver and without a magnetic field. And we can see that all the harmonics are emitted at different times. And also we can see that we have this slope in the emission. This indicates us this emission is cheap, and this is what we call the attosecond. Now, in this second plot, we present the time frequency analysis for this novel scheme. Here we have the circularly polarized driver and the magnetic field. As we can see, in this case, all the harmonics are emitted at the same time, and there is no slope. So in this case, we have achieved free emission, and we can understand why we have this almost Fourier-limited attosecond pulse generation. Okay, to understand why we have this kind of instantaneous emission of all the harmonics, we have again compute the transverse dynamics of the wave packet under the action of the transverse component of the circularly polarized driver field and the magnetic field. As we can see in this case, we have a semi-classical evolution of the ionized wave packet, but we still have this revival dynamics. What is more important here is that we can tune the moment that we have these revivals using the wavelength of the magnetic field. And for a wavelength of 1.6 micrometers, we can see that the revival occurs at the recollision time. In this case, the crossing time of the ionized wave packet with the parent ion can be minimized, and we can understand why all the harmonics are emitted at the same time. And we can understand this cheap free emission. Finally, we present here the time evolution of the population for different states of the transverse harmonic oscillator. As we can see, due to the effect of the transverse component of the electric field, we can push the population to very highly excited states of this transverse harmonic oscillator. So we can understand why we have this extremely broad plateau that we saw a few slides ago, and why we have this kind of semi-classical limit for the evolution of the ionized wave packet. So just to conclude, we have seen how the high harmonic generation spectra can be greatly enhanced by the use of strong and fast oscillating magnetic fields, and even or by the use of circularly polarized driving lasers along the magnetic field, we are able to generate chip free emission. And we don't see any limitation to reach the few or even sub-attosecond pulse generation if we were able to generate even broader spectra. It's obvious that the main challenge here is how we can generate this kind of strong and fast oscillating magnetic fields isolated from the electric field. And it's where we are working very hard to try to enhance this contrast between the magnetic field and the electric field ratio on some kind of structure beams or by the interaction of some kind of metallic antennas, as Luis saw before. So that's all from my side, and thanks for your attention.